So you would have noticed in our last video that we dealt with things called special angles, but we're dealing with 90 degrees and excuse me, so we're dealing with 90 degrees and then 0 degrees, and then we call them special angles. Because we could evaluate them, and we saw that these ratios they take very special whole numbers, which is 0 and 1. The values of the ratios when you evaluate them using the geometric analogies or symbolic analogies to get to the ratios. Now we want to do a generalization of what a special angle is. Now here I want us to first look at the classification of numbers. So here is the classification of numbers. Here they say all numbers that can be represented um, on a number line are called real numbers and can be classified according to their characteristics. Now I want us to look into the number classification. So a number line is a line, it's usually a line that is drawn where you can actually go and put a zero reference. So you put a zero reference, or a starting reference, and then when you're counting from them, all these numbers can be located on that line. So if you draw this line to scale, you can say, okay, this is 1, this is 2, this is 3, and then you can actually say that my 1 is represented maybe by on a scale roller by 10 millimeters. So the 1 unit is represented by 10 millimeters, and then you go to 2, 3, 4, 5, 6, but you can create a number line where you show all these numbers. Now all these numbers, they can be classified or they can be represented on a number line. There are also numbers. Why are we classifying these real numbers like that? What's so special about this number line is because there are numbers that are called complex numbers. So those numbers cannot be represented in a number line. In fact, there are other forms of numbers that cannot be represented in a number line. Like I said, one example that comes into mind is complex numbers. So they can be represented in an arcane form or in an arcane diagram. You can see them in an arcane diagram, visualize them in an arcane diagram, which is in contrast to uh, real numbers, which can be represented in a number line. Now, I want us to go deep here. We have irrational numbers, and then we have rational numbers. So, as you can see here, rational numbers are numbers that can be written in almost fractions that compose whole numbers, and or they can be written exactly as whole numbers. Now, um, if you look at 27 over 4, which is the number that is highlighted there, I think that number is around 6.75. So it does have two decimals, but it can be represented in this format. If you look at E, the number E, or the number root of 2, if you punch that number in your calculator, it just goes on and on and on and on and on and on. In fact, I think it's going to be 1 point something, and then some values, some values, some values, some values continuously. It's an ever-ending number. So it doesn't have a form of representation that can combine two numbers to show it. So in a sense, that what composes rational numbers and irrational numbers, that's the difference. And then inside rational numbers, we look at numbers called integers. Now, these are numbers from negative infinity. These are numbers from negative infinity to positive numbers. You probably know that we have now negative and positive numbers. So all these negative and positive numbers can be classified as integers. And then you have whole numbers. Whole numbers are integers starting from 0 all the way to the positive side. And the natural numbers are integers without 0. That's what number classification is all about. Now that you get what numbers are, we are going to define special angles. Now I've posted also this nice little body of ours here that we're going to be using as we move along with trigonometry. This is going to become very, 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 very fundamental and very important to our discussions. You remember that in the first video also we did introduce this, but this is in a more advanced format. This is quite in a more elementary format, and it gives special angles. So we want to have a generalization here, a sort of generalization of how we can associate and compute these trigonometric ratios, easier ways of computing these trigonometric ratios. And there are really some that are very easy to compute because remember these are dependent on special traits on a special trait of that right angle triangle. And those special traits are actually how the angles inside the right angle triangle are distributed. The two angles, because the other one is already has got to already take one form, which is 90 degrees. Now let's get deeper into this. We are saying that for now we are going to say that special angles. Now, one experiment that we can do here is that we can go back to our last video, and then in our last video, one of our videos, we looked at this here. We looked at this table where we measured these values here from these triangles, and we tried to compute these ratios. And we did a nice exercise here. And in a sense here, there's something that is showing us something very profound here, is that whenever we divide the adjacent side by the hypotenuse, we always get a half. Now is 0.5. Now 0.5 is 1 over 2, which means that the ratio between this side here and that side there for a right angle triangle that has got 60 and 30 will always be a half, which is a very interesting thing because it will always be a number that can be a finite fraction that can be represented as a fraction of two whole numbers, which means it can be a rational number. So that's very interesting because it's easily quantifiable and we can easily compute it whenever we need to do so. We can easily calculate it. So that here is a very important detail because it tells us something very specific about this sort of triangle. And in fact, we are going to write it this side on special angles. Let's look at the 60-degree triangle. In fact, you can draw it yourself. Take a protractor, draw a right angle triangle, make sure that that angle there, like you see in this section, is 60, and then the angle at the top is 30. So you make sure you draw it, make sure that at this angle here is 60 and the angle at the top is 30 degrees. And in every format of every analysis, the adjacent side to 60 will always be of the ratio 1, and then that one will always be 2. So in a sense, if you have A, B, C, this is opposite to 60, this is hypotenuse, and then this is adjacent. So this BC side or this adjacent side over the hypotenuse will always be a half. We saw from this here that it doesn't matter how big the triangle is, as long as it's got these two angles that are the same, 60 and 30 distributed like that, the ratio of this side to that side will always go to a half. We've seen it here, we've done it practically. So that's a very nice little experiment because it means that by observing what we did there, we can actually come and say, well, the fundamental of this triangle is on a ratio of 1 to 2, which means whenever this side is 1, that will always be 2. Whenever this side is 2, that will be 4. Whenever this side is 3, that will be 6. Whenever the side is 4, that will be 8. It will always be on a double basis whenever you do this triangle. That's why I'm saying if you draw it, you can draw the line here, come here, draw two perpendicular lines that are meeting at 90 using a protractor, and then come and measure the angle 60, and then draw a line at 60 degrees that is going cutting that line. And then measure that to make sure that this is also 30 and that this is 60. And then measure this side here and measure that side here, and you'll find that that side will always be double this side. It will always be 2 times this side. The hypotenuse is only 2 times the adjacent for this triangle. Now, what do we call angles that we have this way? In fact, we are going to go to another triangle. Another special triangle is this triangle here. So you draw this triangle here. You can draw this triangle here. Draw a triangle like this. Make sure that this is 90 degrees, and then measure this and make sure that it is 45 degrees. Then if this is 45 degrees, once you finish measuring it, you can take this line, draw it until it cuts that line there, it intersects that line there, and then whatever angle you're going to get there is always going to be 45 because you always have 90 and 45. And then the sum of all angles inside a triangle is always equal to 180, so you can compute that also. and you can measure it. It's going to give you that also on the practical analysis. So or observational analysis. So this is opposite to 45. This is hypotenuse. This is adjacent. Now, there's something very important here that we see. In a sense, if we go and measure this side and that side, they will always give you 1. This side here and that one there will always be equal. They will not always give you 1. But this side here and this side here will always be equal. As long as this angle here is 45 and that angle is 45. As long as you make sure that these two angles are 45, when you're drawing this triangle, it doesn't matter how big you make it, even if you make it even bigger. As long as the angles are maintained as 45 and 45, this here, the ratio of this side to this side will always be 1 to 1. So in a sense, if this is 3, this will always be 3. If this is 4, this will always be 4. If this is 5, this will always be 5. If this is 6, this will always be 6. So that's the basic analogy, the basic idea uh, behind this triangle. It's a special trait of these two triangles, and they are very important triangles. So we can always see here that now when we look at uh, tan of this triangle here, tan of this triangle here, which is equal to or opposite over adjacent, will always be equal to 1 over 1 or which is equal to 1. So not really 1 over 1, but it will always be equal to 2 values that are equal, which means they will always give you 1. So that the ratio will always be 1. And there are a lot of other special features about these triangles. Now, I want us to now look deeper into these triangles, and then we are going to try and find the hypotenuse for this one because we don't have the hypotenuse for this triangle. We do have it for that one, but we don't have it for this one. Now, there is a theorem that we can use to do that. It's called the Pythagorean theorem. Now, we will derive this and we'll learn more about it when we get into geometry. For now, let's just have a look. For now, we'll just kind of give it a special definition of what it is, Pythagorean theorem or Pythagoras theorem, however you want to call it. I think Pythagoras is much more nice. Pythagoras theorem. So the guy who came up with it was Pythagoras. I'm not sure if he was a Greek mathematician or what, but he was a mathematician. So in a sense, what that theorem means, what that theorem states is whenever you have a side, this is the side A, B, C of a right angled triangle. This triangle must be right angled. These sides here, they can be related by A squared plus B squared is equal to C squared. So always the opposite and adjacent side will always be equal to the hypotenuse for a right angled triangle. So this is a very special theorem that you're going to have to keep in mind for now. You don't have to know where it comes from. You're going to get there, but just make sure that you keep it in mind, please. So in a sense, you can come now and calculate what the hypotenuse is supposed to be here. Because you can see that we have opposite adjacent, which is they are represented there by the Pythagorean theorem. So we have a squared, 1 squared plus 1 squared is equal to hypotenuse squared. And then you can kind of take a root here. So you can, to try and make everything the same here, to kind of try and make everything the same and eliminate this square, you can multiply by 1 over 2. But then when you do that side, you need to do this side also. Multiply by 1 over 2, multiply by 1 over 2. In a sense, you're multiplying by 1 over 2 on both these numbers. What I'm doing here is wrong, but I'm just trying to make it simpler. You're multiplying by 1 over 2 on both these numbers. So you could be doing it like this. Yeah, let's do it like this. You multiply by 1 over 2 on both these numbers. So you put them in brackets. Don't do that. And then you also multiply by 1 over 2 also this side. So multiplying by 1 over 2 can be written in a very special way, which is called taking a root. So we say you're taking a root of a number. When you multiply its power by 1 over 2, you're actually taking a root of it. Now you will see why that is the case and what do you mean by root when you get deeper also into exponents. When you're studying exponents, in static algebra. So in a sense here, then we get h, because that 2 is going to go away, the 2 and the 2 are going to cancel, and you'll be left with 1 here and 1 over 1 here, which is 1 over 1 is 1 divided by 1 is 1 times 1, that's 1, so the power will just be 1, so this is the power of 1, and then this will just be equal to root 2. That's it. And then we get the hypotenuse for the 45, for the 45 triangle. Now you can go and calculate the opposite for that one, but it will be root 3. But then you can almost see it that we're saying this side here plus this side here squared is equal to 2. And then we can take this side here to the other side, so we can calculate it. We can say 1 squared plus opposite squared is equal to 2 squared. Now, as you can see, we have opposite squared is equal to 2 squared, which is 4 minus 1. We take that side, it becomes 1 because any number squared to the power of 2 is 1. And then this becomes root of opposite, which is equal to squared, which is equal to root of 3. And then this is called opposite is equal to root of 3, because that root there remove this 2 like we saw here how it does it. So in a sense now we get this very nice analogy here, but then we can continue with it, we can expand it further. Now that we have these two triangles, let's now go and define what special angles are, because we can see that with these triangles all our ratios will be able to represent them in a form of a rational number format, like we described here with our numbers. We'll be able to represent it as a certain number, even if it's a rational number divided by a rational number, but we'll be able to define them in a nice easy to compute or easy to calculate fraction. So let's go deeper into the analysis here. So we are saying we have found these two triangles. Now let's write them down. We're saying we have two triangles here. Okay, it's fine. Let's leave these triangles and then let's check something first. So we're saying we have these two triangles and they have these two features that we like because they can give us these ratios in a very easy format. So now, to make a comparison first before we continue, I'd like you to take maybe sine of 70 and sine of 20, and then compare those with sine of 60 and sine of 30, and maybe also add cos. You can also add cos of 70 and cos of 20. You can also add sine of cos of 60 and cos of 30. You will see that here you get very nice fractions, but here you get numbers that are maybe 1 point something. If you press this on a calculator, you get numbers that maybe that is 1 point whatever fraction it is, sine of 70 is. But then this side you will get very nice fractions because that here is working in conjunction with this triangle that we've derived here. So that's a very nice thing that I want you to do. Complete this, and stop the video, complete this, and then give the answers, and then just compare what you get. That because you will see that these angles are very special because they give you some kind of nice ratios compared to those ones. So that's what we like about this. They are very special and they have some very special they come from very special triangles that are very easy to define. But then what are these special angles? How many are they? Now we're saying these special angles can be defined in a nice way. Remember we talked about integers, and we said integers are numbers from negative infinity to positive infinity. And when we talked about whole numbers, we said these are integers, positive integers starting from 0, including 0. And then talk about natural numbers, we said they are all positive numbers, 0, 1, they are all positive numbers, but without 0. So it's more like you're counting. When you're counting, instead of 1, 2, 3, 4, 5, you are actually only counting natural numbers which fall under integers. So, in a sense, here we're seeing a special angle in the definition of mathematics is an angle that is a multiple. Now, a multiple, it means that you're multiplying a multiple of 45. It's an integer multiple, or natural number multiple, or whole number multiple, or we're just going to call it integer multiple because it can also go to positive, to negatives, but now we're just only going to be looking at positive numbers. So I'm going to say it's an integer multiple of 45 and 30-degree angles. What do we mean by this? We mean that any angle that you get, special angle, any angle that has got this format, that has got 45 multiplied by n, where n falls under the set of integers, or in this case I'm just going to call it natural numbers, or n falls, or n is an element of all integers. And what are these integers? They are from negative. We can start from negative infinity and then go on and on and on and on and on. Or we can just say, we can also neglect the negative side because I still don't want us to talk about it now, and we can just start from positive. But then if we start from positive, it's still integers, but they're only whole number integers. So they become n is an element of of whole numbers. This means that n forms under the whole numbers, and these numbers can be represented from there are 0, 1, 2, 3, 4, all the way up to wherever numbers end. We don't know where they end, so it's infinite. You can count and count and count and count. It never end counting. There'll always be the next number. That's why I would say we don't know where they end. And as you can see there are our whole numbers. W, the input 0, 1, 2, 3, and then all the way up. So if you've got any, this is a special angle. Also, another case of special angles is 30 also times n, and still follow the same procedure. So that means that 0 is a special angle because 30, when n is equal to 0, which will be the first case, then 30 will be 0. When n is equal to 0, which is the first case for 45, 45 will be 0. So that means also 0 is a special angle for both cases. And then when you put 1 there, you'll get 30. When you put 1 there, you'll get 45. So 45 and 30, they are special angles. When you put 2 here, you get 60. When you put 2 there, you'll get 90. So you can see that 90 is a special angle. When you put 3 here, you'll get 90 also. So on both cases, 90 is still a special angle. And then you can continue and continue and continue. You can multiply that by 30, whatever you're still going to get is a special angle. You can multiply by a million, whatever you're getting is a very nice special angle that conforms with that 45 by 45 triangle that we developed at the top. It takes exactly those properties. So let's continue. Now that we've developed a nice understanding here, I want us to go even a bit further. But for now, we'll just stop this video here and we'll continue in another video because it's already around 23 minutes, so I don't want to take a lot of time. So just refresh this and make sure that you understand this. If you have any question, you can post them down on the comments, and then we will continue from this concept and develop a table of special angles and their ratios and their trig ratios and relate them to their trig ratios. So we'll do that in the next video.